And there are a couple of announcements first before we get going on the real stuff. I believe I've announced this before, but I can't remember if everybody was in here, so let me say it again. Any of you go to the Birmingham campus ever? Yeah, okay. On the Birmingham West Campus, the Leon Kennedy Student Center is now closed. Okay? The cafeteria, not open. Okay? It's over in the new Academic Success Center. Okay? They want you to be successful in your eating of your food. Okay? As far as I know, the bookstore has moved over to the Academic Success Center. As far as I know, the Space Center has moved over to Academic Success Center. All of the administrative, all the student services offices have moved over to Academic Success Center. The dorm, housing, everything is over at Academic Success Center now. Leon Kennedy Center is closed. I assume that means even the police department has moved to the Academic Success Center. I haven't been over there to see it. They just sent the email. They said the building's closed. All right. Now, this is the administrative calendar. Usually I don't even bother printing it because most of the stuff on here, I don't even know what they're talking about, and I'm sure y'all couldn't care less either. However, there are a few things happening this month that I thought it was important to remind myself of and remind you about as well. One of these things is, there's actually two coming up. One of them's on here, one of them's not. Next week is going to be a kind of strange week. Okay, this week we had L Day, which was okay, it was nice. But next week is going to be even stranger. On Wednesday of next week, our bosses, who are the Alabama Community College System, the chancellor, has required, I think, that all instructional personnel, full-time instructors, have to be in Montgomery next Wednesday. Okay? That means if you have a class on Wednesday taught by a full-time instructor, check with them on Monday to see if you're having class on Wednesday. There may be a few that somehow get their way out of going. If so, I want to know how they did it so I can get my way out of going too, but I don't think that's going to happen. Because if they do a mini-term course and it's really hard for them to miss, that's equivalent to a whole week of a course, maybe they were able to get out of it, okay? But by and large, most full-time instructors are required to be there. Okay, now if you're in a class taught by an adjunct instructor, yeah, you're probably going to meet because the adjuncts don't have to be in Montgomery on Wednesday. So don't look for me on Wednesday, and really don't look for very many full-time instructors on Wednesday. We're going to be gone. Now, I haven't heard exactly what time the bus leaves, but it's going to be pretty early because I think the meeting starts at 10, and it's pretty close to a 2-hour drive to get there to Montgomery, isn't it? Hour and a half, something like that. So we will be leaving, and who knows if we can get exactly where we need to go in time anyway. Okay, Demetrius is here. What I mean by that is, I don't know if we can go straight to the building or if they're going to take us to a place and then shuttle us in. I don't know what they're going to do down there. All right. Now, if that wasn't enough, Thursday of next week. Now, this I don't think will affect us any, but it has potential maybe a little bit, but I don't think it will. Next Thursday morning at 10 o'clock is the Honors and Awards Ceremony over on the Birmingham West Campus, okay, Arthur Shore's Fine Arts Building, which is also the gymnasium, okay? Now, what does that mean practically? 10 o'clock classes, pretty much most of them will probably be canceled. Again, if they're taught by an adjunct, you may still be having class. I don't know. But I know that me as a full-time instructor, my 10 o'clock class is history because I've got to be there. They require us to be there, all rubbed out and everything. Worse than that, my 8:30 class is not going to have much of it either, because I have to leave shortly after 9, maybe 9:15ish or so, to be over there supposedly by 9:30. So there's no real reason for that, but they still want us to be there early. Okay? So, Thursday, 8:30 classes. Check with your instructor next Tuesday to see if you're meeting at all. You probably will be. If it's adjunct instructor, you almost certainly will be. Okay? If it's a 10 o'clock class, there's a real good chance you're not going to meet. But again, check with your instructor on Tuesday. If it's an 11:30 class, you're almost certainly, well, if it's taught by a full-time instructor, you're probably not going to start on time. You may start a little late, but you probably won't start on time. If it's an adjunct instructor, again, you probably will be meeting. I don't know any reason why you would not. Okay. This class starting at 1:15, if it's not over, I'm leaving. I'm coming back over here. But it's certainly going to have to be over before 12, and that gives me plenty of time to get back here by 1:15. Okay? So, we will have class as normal on Thursday. But check with your earlier classes to see if they're meeting, or if they're starting late or ending early. Check on that. Okay. The rest of this I'll try to hit as we get closer. All right. And one more thing. You see around some of the posted on walls things about NCAS. You see there's a little thing up there, no information, but just a poster about it. What this is NASA Community College Aerospace Scholars. That's what that stands for. They have a really fantastic program that starts in the fall. However, the applications for that are due by the 15th of May. So you got less than 6 weeks to get your applications done. My guess is a pretty extensive application. I haven't seen it, but just because it's really an incredible program. So check into it. This flyer I have has some website information that you can go to and get more information, application forms, that kind of stuff, find out the criteria. I think they do pay you some amount to participate, so it's a pretty nice deal, a very nice deal. The students I've heard from Lawson who have participated loved it. They learned a lot, they worked hard, but they had a great time doing it. Okay? So, check that out if you're at all interested. Okay. Any questions on any of those announcements? All right. I think I got everybody as you came in. 2, 4, 6, 7, 2, 4, 7, 5. Okay. Good deal. Thanks. All right. Now, before we get started today, let's talk about what we're going to do today and what's coming up. And maybe also a little bit of looking behind us as well. So far, I've received one research paper. Folks, we have less than a month to go. In fact, it's probably pretty close to being right at 3 weeks to go. So we don't have a lot of time left. You only have a few weekends left. Be working on your papers. Okay? And also, the first lab of those people who have been in some type of attendance here, I'm still missing 2 first labs, 1, 2, 3, 4, 5 first test, 1, 2 second labs, 1, 2, 3, 4 third labs, 1, 2, 3 fourth labs, 1, 2, 3 second test, and I've just still getting in some fifth labs and a couple that I haven't graded yet. So there's still a few of those missing as well. Okay? Now, the point of all that is we're running out of term. And let me tell you something that happened in the first mini-term class. A student came by my office yesterday. Is there any way I can get this C up to a B? And I said, you didn't turn in, I can't remember now, something like 3 or 4 labs. I dropped, I do drop the lowest lab, but after I dropped, he still had those out. And that brought his lab average down to about a 10 or 11, okay, out of 25. There was a letter grade, because that will do it. Your lab average, you should be getting pretty close to 25. There's no reason not to. He only had like a 10 or 11. That was 1 letter grade gone. So he had B's on his test, but the lab average dropped him down to a C. Nothing I could do about it. I had done just like I just did now, repeatedly say, look, a bunch of you have not turned in your labs. You've not turned in your labs. And he said, is there anything I can do now? I said, no, it's too late. We've already turned in grades. Okay? So please don't be in that situation. It doesn't happen frequently. And he was a good student. Like I said, he had B's on his test. But the lab average killed him. Okay? He may have even had a low A, because 11 from, that's 13 points difference. And he could have had a low A on his test, but the lab pulled him down to a high C. Okay? Not a happy camper he was, and I wasn't happy to have done it, but he's the one that did it. So please get it done. Okay. Now, yes. I can't hear you.
What's the essay supposed to be about?
Anything to do with physics, chemistry, physical science, you choose a topic. Now, it's a good idea to run the topic by me to make sure no one else has chosen that already, but many of you have not done that. I've only gotten 1 paper in and maybe only a few topics. So run something by me, and I'll let you know if it's already been chosen. But there's plenty of things to choose from. People, events, applications, tons of things. It's all out there on the first day of class. I recorded it, and also it's out there, the written instructions on Blackboard. Okay, and Blackboard, you can locate the YouTube videos through Blackboard as well. Okay, now let's talk about where we are today. Okay? We're in Chapter 3. Like I said, we're more than halfway through. Today is no test, so we do have a lab today. So the last 2 hours will be reserved for lab. I can almost guarantee you today's lab will not last 2 hours, but I allow you to have it just in case it does take a little longer. Now, this morning I was running a bit short of time, so I meant to take it down last night before I left, but I forgot to, so I took your lab down to be copied. It's the shortest lab we'll do all term, okay? 1 page, single page. But it will take a while to do it. We will be down in 259, not 253 or 252, not one of these labs, the one at 259, where we were, I think, lab before last, okay? Now, so we'll go till 3:45 and then have the lab, and you'll be out of here, I'm pretty sure, well before 5:45. I'll be here till 6, okay? So if you need to make something up, there's going to be plenty of opportunity today to do so. So plan to do it. All right. Now, today we're going to continue in Chapter 3. We're going to have the second lab, in Chapter 3. And I think we're probably going to finish Chapter 3 today, which means on Tuesday, we're almost definitely going to have a lab, and we'll probably have the test on Chapter 3. If we finish Chapter 3 today, we'll have the test on Tuesday. If we don't finish it today, the test will be Thursday. I think we'll finish it today. So let's see. Now, where we left off, any questions before I get started? Where we left off last time, I think we already had this slide. So this is, but I'm going to use this slide to write on, because example 3.9 we didn't have a chance to do, so let's do example 3.9. A 1.0 kilogram book. Let me get my pen. Okay. 1.0 kilogram book. How much is that? What is that a measure of? That's your mass. Okay. falls from a height of 1.0 meters. And what's that a measure of? They just said it. Height. Very good. H. What is the velocity just as it hits the floor? So we're looking for velocity right as it hits the floor. Now there's a couple ways you can do this one. I'll let you decide. How would you approach this problem?
Multiply
What?
M times H times G.
Times what? G?
Yeah.
Okay, good start. What does that give you?
9.8.
Okay, 9 mgh. What is that a measure of? What is mgh?
Potential.
That is your gravitational potential energy, okay? Very good. And that, like you just said, is 1 times 9.8 times 1 is 9.8 what units?
Meters per second
Second?
squared. Meters per second squared.
That's what G is, but you got M times H as well. M is in kilograms, so it's kilograms meters per second squared times another meter, kilograms meters squared per second squared. What is that? That's a perfectly good unit. Kilogram meter squared per second squared. Okay? Let's just leave it like that. That actually works pretty well. And that is your gravitational potential energy. But you do need to know, what is that? What is a kilogram meter squared per second squared? It has its own name. After James Prescott. Joule. Okay, those are joules. So I'm going to put joule. Okay. That's what a kilogram meter squared per second squared is. Okay? So that's the gravitational potential energy at the top before you release the book or before it falls. That's its gravitational potential energy. What is the velocity right before it hits the ground? How are we going to get that?
Multiply
What?
the MGH.
Okay, we already did that. We multiply M, which is 1 kilogram, times G, which is 9.8 meters per second squared, times height, which is 1 meter. That gave us kilogram meter per second squared times a meter is meter squared per second squared. So we've already multiplied that. That's your GPE at the bottom. How do we get velocity out of that? Anybody? Where do we go from there? Now, this is one good way to work the problem. There is another way, but we'll do that in a minute. How do we get velocity out of that? Actually, your units almost tell you. Not quite, but close.
Multiply
What?
distance times time.
We've already done that. We multiply kilogram meter per second squared. You know, we got it. Now, time, we don't have a time in here. No, well, I don't see one. Okay? This is the potential energy, the gravitational potential energy 1 meter above the floor. Okay? That 1 kilogram book, this is its gravitational potential energy 1 meter above the floor. Right before it hits the floor, how much gravitational potential energy does it have? Right as the height is approaching 0. What's the gravitational potential energy then? 0. So where is the energy gone? You can't create or destroy energy. Where is that energy gone? It's because, see, energy is never created nor destroyed. But it can be converted from one form to another. Where did the energy go? V is the velocity. But what kind of energy is associated with velocity? If something has a velocity, that means it's what?
Accelerating.
It doesn't have to be accelerating, but it is moving. What is the energy of motion? Help me, somebody. The energy of motion. Kinetic energy, of course it is. And what's this formula?
1/2 times M times V squared.
Perfect. Okay? That's perfect and stuff got here too. Okay. All right. Now, basically what's happened here, at 1 meter above the floor, all the energy that this book had was gravitational potential energy. But when it started falling, now it's losing its gravitational potential energy, but that's now becoming kinetic energy. So right before it hits the floor, all of this gravitational potential energy has now become kinetic energy. So this is now your 9.8 kilogram meters per second squared. Meters squared per second squared. Okay? Now, I've got to sneeze, sorry. What we want to do is solve for velocity. Right? So what can we do? First thing we've got to do, multiply by 2, okay? That will get rid of your 1/2. So you have mv squared is equal to 19.6 kilogram meter squared per second squared. All right? One more thing you got to do before you can solve for v. What? Divide by m. And your m is 1 kilogram. 1.0 kilogram. Okay? Well, there goes your kilograms. And 1 divided by 19.6 is still 19.6. Here the m's go out. So now we have v squared is equal to 19.6 kilograms left. So now we have meters squared per second squared. Okay? Hey! How are we going to get a v out of v squared? Take a square root. Okay. And we'll take the positive square root because this is going in a positive direction. So it's going to be v is equal to, pull out your calculator and take the square root of 19.6. Something between 4 and 5. Square root of 19.6. 4.4? Yeah, that seems like that'll do. 4.4, what units? When you take the square root of this, second, meters per second. You also take the square root of your units as well. A meter squared becomes meter, and a second squared becomes second. 4.4 meters per second. That's the speed just before it hits the ground. Okay? Now that was to me, the logical way to do the problem. If you're into just memorizing formulas and equations, then you could have done it this way. Okay, sorry about that. Let me clear my scratch. Can I clear it, or do you need it longer? Okay. Sorry, I ran out of room at the bottom, had to move to the top. Got it? Okay, so I'm going to clear this. Is that okay? All right. The other way you could have done it, if you're just into memorizing formulas, is this way. This works it out for you. The potential energy, gravitational potential energy lost at the top equals the kinetic energy gained at the bottom, which is what we just said. The energy at the top was mgh, the energy at the bottom was 1/2 mv squared, just like we said. And when you solve for v, your 2 comes over here, the g stays, the m's divide away, and you take the square root, and the v is equal to square root of 2gh. So let's do it the short way, and just do is equal to the square root of 2 times 9.8 meter per second squared times h was 1.0 meters. Okay? and that gives you exactly the same number, the square root of 19.6 meters squared per second squared. And when you do it, you get 4.4 meters per second. That is your final velocity. So that was a little shorter because we divided out the m's and didn't even enter those in the picture. And this gives you your answer. It's not as, to me, it's not as clear conceptually that gives you that. That's just memorizing the formula and using it. The other way actually helps me see why it works this way. Okay? But if you see the whole process here, you see the same thing. All right, so we got 4.4. Now, in your text, if you've noticed this, okay, if you've noticed this, they've got something a little bit wrong with the answer. Anyone notice?
What page you on?
That's on page 75.
It's what line? You talking about the answer?
The answer.
M times S.
They say m times s, it's m divided by s. It's meters per second, not meter seconds. So they did get that wrong. I made a correction in mine. Be sure you do it in yours. All right. Now, let's back up again. Clear this. Can I clear it? Okay. Let's do example 310. Oh, which would have left it. Sorry about that. It says, what is the kinetic energy of a 1 kilogram book just before it hits the floor after a 1.0 meter fall? And this, again, is wacko, the way they answered it. Okay? What's wacko about it, they took that answer, V, of 4.4, which was a rounded answer, and then plugged it back in the kinetic formula, Ke is equal to 1/2 mv squared, and they came up with 9.7 joules. But guess what? We just calculated what the kinetic energy was. It was 9.8 joules. So what they've done, by using a rounded answer and recalculating it, they came up with decimal short, which there's no reason to do. All you had to do is look at it back earlier in the problem and say it was the same as kinetic energy loss, potential energy loss, and that was 9.8. So their answer is sort of wacko. I wouldn't mark it wrong, but why go through the work of extra work to get a wrong answer? Use what you already had. It was 9.8, not 9.7. Okay? So that's a little bizarre. Okay. Now, the next thing they're going to show here at the bottom of page 75 of the left-hand column is a great diagram that I don't think they show on the slide set. I can't talk. No. So I want to hold it up for you. I know people at home won't be able to see this, but sorry about that. You should be here, okay? Here is the diagram. This shows some of the ways that energy flows, okay? Now, where do we get most of our energy here on Earth? Sun, absolutely right. What's going on in the sun that gives us energy? How can the sun, way out there, 97 million miles away, be giving us energy? What's happening on the sun? People who had physical science 1, you sure should be able to answer this one. What's going on in the sun that gives us the energy we get from it? Radiation. Okay, radiation is coming from the sun. Where's that coming from? Yes, what's happening in the core? Massive nuclear reactions, fusion reactions. Hydrogen is fusing to become helium, okay? And it's been doing that for about the last 5 billion years, they estimate, and it's only got about 5 billion years left to fuel, but I don't think it'll bother me any because I'll be long gone before that. So, the nuclear reactions on the sun are either transmitted to Earth as radiant energy, but we also produce some nuclear reaction here on Earth by taking radiant energy, light energy, and using laser-induced fusion. Okay, that's pretty minor, but it does happen. So that's how you can go back and forth between nuclear and radiant energy, radiation. Okay? Once the radiant energy reaches the Earth, what does it do? Well, some of it enters those little green leaves out there through photosynthesis, and the radiant energy becomes stored chemical energy. Okay? But you can also burn that wood or leaves or twigs or sticks, oxidize it, and it becomes heat again, which is a form of radiant energy. So that one goes both ways as well. I can't hold this up forever. Okay? Now, another thing radiant energy could do, that radiant energy could be captured by a solar cell and become electrical energy. And where was I driving not long ago? And I looked out and just saw lots and lots of solar cells on the rooftops. I think it's when we were driving down to Louisiana. I believe we had just gotten into Louisiana on our way to New Orleans, and just saw lots and lots of rooftops with the south-facing roof, solar cells up there, solar panels up there. So those people are being really smart and getting energy directly from the sun as electrical energy. But on the other hand, you can turn on the lights and use electrical energy to become radiant energy, electromagnetic radiation. So those arrows go both ways. Or you could take that radiant energy from the sun and change it to mechanical. And how you do that basically is a sort of a long, involved process. But actually, I've seen one of these. I haven't seen the inner parts of it working. But when I was at Georgia Tech, this is decades ago, and the dorm that I was living in was a new part of campus. And when I was walking toward the student center in the older part of campus, went right by this big, long apparatus. And what it was a parabolic-shaped mirror facing sort of toward the south, okay? Big mirror, and right down the center, which would have been the focus of that parabola, was a pipe. And in that pipe, they either were running water or they were running some other liquid that when the light waves from the sun were captured by the mirrors, focused on the pipe, it heated up the water or whatever liquid was in there into a gas, into steam, and they could then do mechanical work with that. Okay? So that's what they call a heat engine. Okay? So radiant energy can be used directly to be by a heat engine to produce mechanical energy. All right? Or a device can use mechanical energy to rub things together and produce heat, which is a form of radiant energy. So it goes both ways. Okay? Now, let's go to chemical. Okay, over to chemical. We've already done chemical to radiant and back and forth, but let's do chemical down to electrical. Well, how does that happen? One way is a battery or a fuel cell. Okay? A typical battery has in it two different layers of material that have different electronegativities, and that then creates a potential difference, and that then can operate a computer, it can operate a flashlight, it can operate a cell phone. Second? remote controls, all those kinds of things. I bet you, goodness gracious, DeAndre, you have a battery in that device? Yeah, of course you do. That's what's enabling him to listen, okay? So, sure enough, chemical energy can be used to form electrical energy. Or electrical energy can be used to do chemical. And they mentioned here electrolysis or charging a storage battery. Your car is doing this all the time. When you go to start your car, your battery is providing electrical energy to convert that to mechanical energy. But when you're running your car, you're recharging the battery by using mechanical energy to turn your alternator, which is in a sense a generator that recharges the battery. Okay? So you're doing that all the time too. So let's do chemical to mechanical. This is basically your heat engine as well. Okay? But this time we're using chemical energy. For instance, this is mechanical. I operate a lawnmower. How does that work? Burning fuel, chemical energy, getting it to turn the blade so I can cut the grass. Do it all the time. Your car, chemical energy to mechanical energy. That's why it runs. That's why it rolls. That's why you get kinetic energy. Going the other way, of course, mechanical energy, when you're doing all those things, when you're burning that fuel oil, this is sort of a bad example. Seems like that's not the, they say friction and burning. Burning would be going the other way. Friction would be this is a little harder to picture, but recharging the battery by turning something. Your car is doing it, so I guess that we've already hit on that. Okay. Then let's see, electrical, we've done radiant chemical and stuff. So all we got left is electrical to mechanical. Of course, that's pretty obvious. If I wasn't running a gas-powered lawnmower, I might have it plugged in and running an electric lawnmower. That is taking electrical energy, turning it to mechanical. Or any of these power plants that we have around here are taking mechanical energy, whether that's from moving water or from burning fuel oil or natural gas or coal or anything else, and taking mechanical energy, making it into electrical. So it's a great diagram because it shows just a few of the various pathways that energy always never is destroyed or created. It just changed from one form to another form to another form to another form constantly. Okay. Now, and that was all under energy conservation. All right, now let's look at the flow of energy, which in your text, there's a couple places where it is. There was energy conversion. Well, I guess not. Oh, yeah, 3.3, the whole section is called energy flow. So this is sort of a summary slide showing just a few of those ways. There also the energy transfer on the top of page 76, that's sort of also here. And this is just sort of a simplistic drawing of what in the world we were just talking about. Energy, again, and this is same from the last slide, never created nor destroyed. However, it can be and always is converted from one form to another form to another form to another form. Total energy remains constant. And they showed this in this picture. The sun up here, nuclear energy in the sun, nuclear fusion reactions going on constantly, always sending out all this energy into the solar system. we pick up just a tiny little bit of it, like we pick up Kelvin, okay? And fortunately, our atmosphere blocks many of the dangerous things, like the gamma radiation and the X radiation and cosmic radiation that would kill us, and only allows the light energy, the electromagnetic spectrum, the light spectrum from violet to red. A little bit of ultraviolet gets through. That's what causes the skin cancers, cataracts, those kind of things, sunburns, that kind of thing. But most of it is the good stuff, and then there's a little bit of heat energy, more is escaping than coming in. But anyway, the light energy is taken up by the tree. Well, let's just imagine that's an apple tree or a pear tree or some sort of tree like that is producing a fruit, and the people eat the fruit. So this is nuclear to radiant, radiant to chemical, because the trees are capturing that radiant energy, light energy, and photosynthesis, synthesizing a chemical. We eat the fruit. I didn't get to eat my apple today, but I will after class. And that gives me the energy to get home. Now, I won't be riding a bicycle because it's too far, but I like riding a bicycle, and that changes to mechanical energy. Mechanical energy, if you've ever ridden a bike, you know, just like your car gets hot, you get hot, okay? You produce heat, and that goes back up into radiant energy. Now, whether that heat is useful energy, that's another issue. Many times we cannot capture that and reuse it. Most of these go both ways. That one's the one that a lot of times we have trouble using that wasted heat energy. Now, do any of you drive a hybrid car? You do. Okay, what kind? Prius?
A Nissan Altima.
A what?
A Nissan Altima.
Oh, okay. Now, do you know if it has what kind of braking system it has? You might not. Okay. I know I think it's the Toyota Prius, but probably the others too. Their braking system, see, on the rest of us who drive just regular cars, what's your braking system? Friction. You have brake pads and a brake drum, and when you do those together, they slow you down by friction, produce an awful lot of heat, wasted heat, that we can't really recapture and use again. But a lot of the hybrid cars, their braking system, they are generators. Their brakes are generators, and when you're turning a generator, you're using mechanical energy to produce electrical energy. So they use, and I bet you yours does too, that generator slows the car down because it's using the energy, the mechanical energy, the kinetic energy of the car to regenerate electrical energy, which it goes back and recharges the battery. So every time, if you have that regenerative braking system, every time you step on the brake, you're recharging your battery. A much more efficient way of doing it, because then you can use that energy to keep you moving again. So it is a good deal. And evidently, when I broke them, they broke. Okay, no. Okay. All right. So that's just sort of a synopsis slide showing some of these transfers of energy. Okay. Now, the next topic, 3.4, is energy sources today. Now, this is sort of an old slide. I think the one in your book is a little more current than this one, so I'll tell you the places where to update it. But I bet you the one in the book is older than what is really happening today. What's that? Yeah, I know it's flipped some, but the percentages have changed too. Okay? So petroleum, when this slide was done, was 40%. Right now, when the published the book, it had dropped to 36%. I bet you that we probably dropped even less. Now, I'm not saying we're using less petroleum. The percentage is less. Okay, we're probably still using as much or maybe even more, but we're just big energy hogs, so we're just using more, but the percentage has gone down. Okay, so next step, and that's 2/5. Okay, close to half. Okay? And one thing that's gone up is natural gas. When this was done, we were only 23%. In your text, we were up to 27%. Now, the reason for that is they've developed new ways to capture natural gas out of shale oil, and rock like that, and this fracking and things like this. They have come up with some new ways to extract natural gas. So we are becoming far more energy independent than we were when this slide was done, okay? And mostly of that is natural gas, okay? Now there, coal was 21%. You notice in the book it's dropped to 18%. And from what I understand from listening to the radio and stuff, it continues to drop, okay? So I bet you we're less than 18% now. Now, why is that? Because we're interested in the environment? Well, some of us are, okay? A few of us are. But guess what? Because of these new ways to get natural gas, this has become cheaper than coal, okay? And because it's become cheaper, companies are going to it. Even though some politicians are promising to bring coal back. Ridiculous. No one wants to pay more for a dirtier fuel, okay? The good side of that is natural gas burns so much cleaner than coal does. You have almost no ash from natural gas. You have quite a bit of ash from coal. You have a little bit from petroleum, very little from natural gas. Still produces greenhouse gases, carbon dioxide and stuff, but it's a lot cleaner fuel. So some people are changing to natural gas because they're interested in the environment. Most of them are changing because it's cheaper. Okay? And guess what? That's not likely to turn around anytime soon, no matter what politician says. Okay? Now, at the time the slide was published, nuclear was at 8%. Now it's, on the book, it's still 8%. Now, part of the reason for that, we are doing more nuclear than we used to, but the percentage hasn't changed. Part of the reason for that is many years ago, I'd say many decades ago, two events happened, okay? And then more recently, a third one happened. One of those events was Chernobyl. Does anyone know what Chernobyl is or was? Well, back then it was the Soviet Union. It was mostly Russia, but it was the Soviet Union. And the Soviet Union had a big nuclear power plant in Chernobyl, which is actually in Ukraine, but it was part of the Soviet Union. Now, the Soviets typically built big, built fast, and built cheaply, as cheaply as they could, okay? They didn't have the environmental protections we did. They didn't have the safety protections we did. And their plant at Chernobyl, and I don't know all the reasons why or behind it, they had a meltdown which was so major. I mean, it killed a bunch of people and it damaged a bunch of people. It wiped out this area. Nobody lives in or near Chernobyl anymore. It's still emitting such high levels of radiation, no one can live there safely. Now, let me give you a little backstory on it, too. It's somewhere in the book, or y'all can look it up on your phone. What happened at Chernobyl was, I think, around the 1980s, if I'm not mistaken. Does anyone happen to know? Nuclear, I don't think they list here. I'm just going to guess it's around the 1980s. Huh? Yeah, but I believe it's 1980s. Okay? Like I said, many people were killed, many people were damaged pretty badly by the radiation. Okay. There was a kid, okay, let me give a little background to it. a lot of people having died, there were a bunch of orphans left. But there were also people who survived. And then when they went to have kids, a lot of times their kids were damaged. They weren't even born when Chernobyl happened, but they damaged the parents when they were young, and then when they had kids, those kids were damaged. Okay? And back then, maybe still, when that happens, sometimes the parents say, I can't afford this damaged child. I can't afford the medical. I can't afford the extra it's going to cost to educate or to train them or whatever. They just drop them off at an orphanage. And unfortunately, a lot of that happened. Now, good old folks in the U.S., sometimes I badmouth our country because I don't think we do as much as we should do, but we do an awful lot more than most. And there was a group of churches, I believe it was, that got together and sponsored camps that they would bring over kids that lived in the Chernobyl area that were still being exposed to radiation because the parents couldn't afford to move any further away. They'd bring them over for a summer or at least a month in the summer and host them here in the U.S. just so they have 1 month or 3 months to grow up in an environment without that radiation. And that greatly improved their cognitive ability, their physical abilities. It was wonderful for them. Okay? Other groups went to Ukraine and went to orphanages and actually adopted the kids that had been dropped off. And it's probably been close to 5 years now, maybe a little longer, that there was one of these kids, and I had seen him as a very, very young child, just a delightful little kid, okay? Because friends of ours knew the pastor whose daughter had adopted the kid. And we saw him when he was very, very young, maybe 3 or 4 years old. He was developmentally behind what other kids would have been, but he was a bright little kid. He had some learning problems. He had some physical problems. In fact, one of his physical problems was he did not have a right arm. Was born without a right arm. His parents had been children when Chernobyl happened, but they were exposed to enough radiation that their reproductive systems were damaged enough, not knowing when they had the child, they just sent him to an orphanage. He had a hair lip. He looked a little strange and he was missing an arm. I think he had one finger sticking out of his shoulder. That was it. I mean, it was just really bizarre. Yeah. So anyway, this family adopted him here in Birmingham area, and they raised him, and he was a delightful child. But he did have some learning problems, and he was trying to go to Jeff State and get his degree in physical therapy technician. He wasn't trying to become a physical therapist, just a technician helping the physical therapist, because he had to learn to do everything with one arm. So he knew what it was to have to go through physical therapy. And he couldn't pass his math courses at Jeff State. And his adopted parents found out through our friends that I taught math here, so they said, could he come up there? Can you think you can help him? I said, sure, send them out. So I recorded classes, and they got to, the mother and the father got to listen to the classes at home and help him with his homework. And he was able, he wasn't a great student, he was a great kid, wasn't a great student, but he managed to pass his 100 and 112. He came back the next year to do 112. Sat right back there in the corner seat back there. Delightful young man. And he's doing everything he can to help other kids who have physical disabilities because he knows what it's like. But the point is, his parents, if they were even born at the time of Chernobyl, they were young kids. And they were damaged enough that he was damaged and they gave him up. So it's a serious business, this nuclear energy. Okay? Now, that was one event, Chernobyl. There was a second event that happened within just a few years of Chernobyl, and that was called 3 Mile Island. And that was here in the good old US of A. Even though we had many more safeguards and safety features and everything else in our systems, nuclear power systems, we still came close to having a Chernobyl type problem. It was like Chernobyl, but it got shut down much sooner, and nobody lives on 3 Mile Island anymore, but at least it didn't damage a whole community for miles and miles around. Okay? The third one happened during your lifetime. Do y'all remember Fukushima? That was a tidal wave, natural disaster. An underground earthquake created a tidal wave. The tidal wave hit a nuclear power plant. Nothing they could have done to keep that from happening, and they built in, this was in Japan, as many, if not more, safeguards than we did, and still lost the plant. They captured, there's many incredible stories about that. One was, you see, when the tidal wave hit, it knocked out all the electrical power. And that was electrical power generating plant. They couldn't generate because, the tidal wave hit. Well, when the tidal wave went out, the pumps went out. And the power went off. The pumps went out. When the pumps went out, they couldn't cool the reactors. And when they couldn't cool the reactors, they overheated, and it was a disaster. Now, it probably was as bad of a shutdown as Chernobyl was, but because they had so many safety precautions there, not nearly as many people were affected by it. Because Japan is a very small island, and it has tons of people on that. It's a series of islands. But they still had to go back in there and shut down a damaged nuclear power plant. And this was incredible. Some of the older Japanese men who had long since retired from that plant said, wait, don't send these young men in to do this. You're going to damage them for life. They said, our lives are mostly behind us now. We don't have much to lose. Send us in. And those old geezers, but who knew what they were doing, went in and did as much cleanup and shutdown as they could. They probably have since died, but they basically gave it up so that the younger generation wouldn't be as damaged. Incredible. So, I'm sorry I got off of the nuclear. That's one reason nuclear power has not expanded. Now, in all places in the world that you might have thought would be resistant to nuclear power, that would have been Japan. Because Japan is the only place on the earth that has had, well, not the only place on earth, only place on earth that intentionally atomic bombs have been dropped. By us, okay? We dropped at Hiroshima and Nagasaki and killed tens of thousands of people, okay? So you would have thought Japan would have said, no, we don't want anything to do with nuclear. But you see, Japan has no petroleum, no fuels. They had to import everything. And they said, no, let's go with nuclear. And they built their plants safely. They built them well. But guess what? They still had a disaster. So they've started shutting down most of their nuclear reactors. Now, we shut down we shut down a few, but we didn't build any new nuclear power plants from the date of 3 Mile Island until very, very recently. And the first one I know about that's been built actually was an existing nuclear power station. They brought on a new reactor. First new reactor to be approved since 3 Mile Island. That was probably nearly 3 decades, maybe even longer. And the reason I know that, it was in my home county in Georgia where I grew up, in Burke County, is the Vogtle plant. They opened a new reactor, and they built new power lines that you can see from the farm where we still own. My parents have died, so my brothers and sister now own pieces of the farm. And from my brothers and sisters' place, you can see the power lines that are going from Plant Vogel, the new lines they have to ship out the power. Okay. So, after nuclear, the next is, on this one was hydro. Okay? On this slide, they don't show hydro. They just show renewable. So hydro is included in renewable, as is biomass, as are geothermal and solar. So if you combine these three together, that's 3, 3.5, and a half, that's 7%. On this one, it's 9%. It is increasing, but it's awfully slow. Now, I bet you nowadays it's a little bit more than that. Okay? So, however, we'll talk about some of these more specifically later. I'm probably saying too much now. If you look at history, way back in history, and that doesn't go too far back either, about the mid-1800s or so, primarily we burned wood. If you think of when this country was first founded, okay, mostly the biomass was wood, okay? Now, when the first railroads were built, what did they run those steam plants with? Wood. They were feeding those furnaces with wood, making steam. The steam then turned the motors that ran the trains, okay? But after a while, they found out that coal was much more efficient, less ash, still pretty dirty though. They went from wood to coal, okay? And so did power plants, okay? Then they went from coal to petroleum, and with the increasing industrialization, because petroleum was cleaner and more efficient as well, and now they're going from petroleum to natural gas, okay? Natural gas is still lagging behind, but it's catching up with increasing industrialization. So how can they say all that? 89% can be traced to photosynthesis? Well, yeah. Where did petroleum come from? We'll talk about it in a few slides. Where did the coal come from? We'll talk about it in a few slides. Where did natural gas come from? The same place these did. These were plants that captured that energy from the sun millennia ago, tens of thousands of years ago, hundreds of thousands of years ago. Photosynthesis has been happening forever, has been storing that in petroleum, coal, and natural gas. So the percent that's not, nuclear is not photosynthesis. Biomass mostly is photosynthesis. Hydro is not photosynthesis. Geothermal and solar is not photosynthesis. So 89% can be traced to photosynthesis. Okay? Now what are the uses for energy today? About a third of what we have is for heating purposes. Heating of homes, heating of buildings, that kind of stuff. 2/3 are burned in engines and generators. That's our automobiles, all our forms of transportation, and all our generating capacity of electricity. Okay? That's where we use our energy today. In the past, it was mostly heating and cooking, and that was about it. Everything else was mechanical, horse-drawn, whatever. We have really come along. So let's look at these individually. And again, I've said too much before. Petroleum is mostly oil, most of the time from oil-bearing rock. Now that was a surprise for me because I just always pictured it. They drilled down into a pot of petroleum, and they went gushing into the air. Well, actually most of petroleum comes from oil-bearing rock. They have to extract the petroleum from it, okay? Now, where did this petroleum come from? Like I was just saying, organic sediments. And what organic means, coming from living beings. Mostly trees and plants. Though some is animal waste and stuff like this too, dead animal and stuff like that. But it's transformed over time. And when it says over time, they mean lots and lots of time. As I said, centuries probably isn't long enough. Millennia is closer. Tens of thousands of years, hundreds of thousands of years, millions of years. Well, that's not just been time. Bacteria were involved. Because you see that organic sediment, the trees, the limbs, the leaves, that kind of stuff, has to be broken down by bacteria to form simpler materials. And then, as more and more get piled on top and on top and on top, pressure forces that closer and closer together. The more pressure you got, the higher temperatures. So the combination of pressure, temperature over time, with bacteria contributing on the front part of that, that's where you get your petroleum. And that's why it's an oil-bearing rock, because those rocks were formed by pressure, temperature over time. Now, they're grouping in number 3 with number 1 here, natural gas formation, very similar, but generally at higher temperatures and higher pressures. So wherever you have petroleum, you usually have natural gas as well. That's also from oil-bearing rock. And the thing is, today they've got new techniques for getting that natural gas out of the rock. Part of that is the fracking. They have other means as well. Petroleum and natural gas are often found together. Okay? Just said that. Supplies are limited. Okay? 25% are coming from offshore wells. At the time of the printing of the slide here, more than 50% was imported. My understanding today, we're at less than 50%. That doesn't mean we've reduced the amounts of imports. It's just the percentages have gone down because we're producing more in the U.S. And offshore wells. Does this ring a bell? It wasn't long ago, probably about a decade or so, that we had the Gulf oil spill. Y'all remember that? Pretty disastrous. I did not realize the Gulf of Mexico went down as much as 1 mile. That oil well was down there about, or I think a little more than a mile deep. And at more than a mile deep, the temperatures are very close to freezing. I always thought the Gulf of Mexico was a hot tub of water because it's really almost always pretty warm water. But at a mile down, hey, not enough sunlight or anything else, and the cold water stays down here. The warm water is all at the surface. It was cold. And at those temperatures, at that depth, how in the world do you stop gushing petroleum from coming out of the ground? That was a major engineering disaster, but it was a major engineering feat to get it to stop. But it took them months and months of millions of barrels of oil a day escaping into the Gulf of Mexico. Not a good prospect at all. We shut back a lot of our offshore drilling then to try to improve our procedures, to try to make it sure that it's not going to happen again. I guarantee you it will happen again. I mean, equipment gets old, things get weak, it's going to happen again. Now here's the part that bothers me. If it took millions and millions and millions, hundreds of thousands and maybe up to millions of years to form this stuff, and we're using it as fast as we can get it out of the ground, there is a limit to it. This stuff was being formed thousands of years ago, hundreds of thousands of years ago, and we're using it as fast as we can find it. Okay? Even in places like Saudi Arabia, Nigeria, Venezuela, where they have large reserves of it, we're using them up as fast as we possibly can. So therefore, this is not a solution, folks, because it took hundreds of thousands of years for that to form, and we're using it as fast as we possibly can. We're going to run out at some time. It probably won't be during my lifetime. It may not be during your lifetime, but it's not going to be many generations in the future before we can't count on this fairly cheap resource, even if it's a dirty resource. Okay. But petroleum and natural gas aren't super dirty, but they do produce greenhouse gases. Coal, however, is another issue. Now, notice how it begins? Same way before. Accumulated from plant and or animal materials, processed over time by pressure and temperature, and microorganisms, bacteria, and stuff like that. Now here, it's a slightly different process, though. You start with peat, which is basically a lot of organic matter. I usually think of this as swampy type areas where it just built up over time, and you don't have as much oxidation, so you have more reduction going on. That forms another mineral called lignite, and then this lignite becomes subbituminous coal, and finally becomes bituminous coal. Now this is the good stuff, okay? A lot of the coal that we do around here, we probably have some bituminous, but a lot of our coal around here is anthracitic coal, which is a lot dirtier. It's not nearly as clean. Now coal is never clean, but bituminous is much cleaner than anthracite. So we don't burn most of the coal. If you drive on the interstate, right before you get to the Alabama Adventures or Splash Adventure, whatever the exit is, you cross over a fairly new overpass there, and you'll see coal cars some days just as far as you can see. When you go up 22, the new interstate, going toward Jasper, you'll see sometimes coal cars just as far as you can see as you pass over probably the other side of that. We do a lot of coal drilling here, okay? But most of that we ship to Central America, South America, or other places that don't have environmental controls like we do. I know, but we still burn a lot, especially on 22. Look at those stacks sometimes. They're pouring it out. And some of that coal is the coal they're bringing in from Wyoming or other places to burn here. Some of that coal is coal they're shipping out to go to other places that don't have it. Okay, so anyway, that's it. Coal always contains impurities, even the good bituminous coal. Minerals lead to ash, so there's always ash. Okay, excuse me. Okay. Coal always contains sulfur. Okay. The bituminous coal has less sulfur than anthracitic coal, but it still has it. The sulfur, when it burns, because when you burn the coal, you're also burning the sulfur. When you burn sulfur, it becomes sulfur dioxide. You combine sulfur dioxide with water, which it meets in the air, and guess what you have? Sulfuric acid. That really strong acid that eats your clothes. If you spill battery acid on it, it will eat up clothes in no time and burn skin like crazy. Okay? That's what's falling out of the sky when it rains if you're running a coal power plant. Now, a few years ago, I had a Toyota vehicle. Had it for probably pretty close to a decade. Good vehicle. And I carried it to Jim Limbaugh that's where we bought it, and that's where we had it serviced and stuff like this. And the old guy who would do the transport, bring me onto campus or pick me up from campus, whatever, he had been in the area a long time, and he talked about, I can't remember which day of the week it was, but on one day of the week, all the housewives knew this, that they were going to blow the furnaces at the steel plants and these other places because they were burning coal. And the coal, all this ash and other pollutants would clog up the system, so they would put high pressure steam in there to blow it out. And all the ladies knew, get in your laundry before that happens. Because if you left your laundry on the line when you got it in, it was perforated. Okay, everywhere the ash hit, it would eat through the clothes. Okay? Yeah. So all of these are called fossil fuels because they all took hundreds, if not tens or hundreds of thousands of years to form. Fossils could be found maybe in some of them, but not all of them, but they came from long, long, long times ago. And there's still a lot of it down there, but it's harder and harder to get to, more expensive to get out, and some of it's not as good as the stuff that we've already got now. So you're going to have more and more problems. Okay? Those are our fossil fuels, and we live on them. We are trapped by them today because we're such energy hogs. We can't do without them. Okay? Now, much cleaner, this is one of the renewables, is moving water. Okay, this is what, and we are so fortunate here in the Southeast to have lots of places where we have all these great hydroelectric dams. The Lewis Smith Dam up pretty much, what's the county Jasper's in? Walker County or near Jefferson County line. There's a dam there. They produce hydroelectric power. Wilsonville. I mean, there's all around us. There's all these lakes. Look at a map of Alabama, especially northern Alabama. You see all these lakes there. Gunnersville. They're all hydroelectric. Okay? This is a pretty clean energy because what it comes from, water evaporates off the oceans, goes into the atmosphere, comes over land, then falls in the high levels, and then as it's running downhill, we back it up with a dam, and then let the running water, gravitational potential energy of that water, convert it to electrical energy as it turns the turbines. These are water turbines. But back when they built all these, they were a pretty major source, and we in the Southeast paid some of the lowest electrical bills in the nation. So right now, the hydroelectric plants generate only about 3% of the U.S. total energy consumption. The reason for this, two reasons. Number one, we use so much more than we used to back when they were built. But number two is there are not many more places you can build. Okay? Because most of this land, like up there in Walker County, that was a pretty poor area back then. So they could buy up the land pretty cheaply and put a dam in, back up the water, and buy out the farms or other places that people would live, and they thought it was a pretty good deal. Nowadays, it's really expensive to try to put the dam anywhere. Not just the building of the dam, that's expensive enough, but buying up all the land, that's begun. So the growth potential is limited by decreasing availability of new sites. How about South Alabama? There aren't many dams down there. But if you think about it, South Alabama is flat. And if you could build a dam, you're going to flood huge areas. And nobody wants to have their homes flooded. So, and their farms flooded. So no, there aren't many new sites to happen. And even some of those that might be, they're such beautiful areas now. People enjoy getting out to nature. They don't want this done. Now, there was a movie done back when I was in college. No one remembers it for its environmental part. They remember it because of the gross part. But it was called Deliverance. Anyone ever heard of that? Burt Reynolds was the star of it. Had some pretty gross stuff in it, but it was really the story of a group of men going to paddle the river one last time before the hydroelectric dam filled it up. But it wasn't the best of stories either. Okay. All right. Nuclear. Now, this is based on the sun. What's going on is nuclear fusion. Light molecules atoms are being fused into heavier molecules. Hydrogen, the very lightest, and the helium, the next lightest. Okay? Actually, that's a pretty clean process. Has a lot of radioactive material coming out of it, but it's clean. Okay? If you don't count radiation dirty. But here on the Earth, we can't do fusion very easily. It's really hard to do. We have done it, but we do it on fission. What fission takes is very big atoms, bulky atoms, atoms that are unstable, and splitting them. Uranium is way up there in the periodic table. Plutonium is right next to it, or really close to it. When these split, the byproducts of this is pretty nasty stuff, okay? And that's radioactive for millennia to come. So what they're having to do now is every place they have a nuclear power plant, when they use up the uranium and plutonium, which takes a while to use, but not just at power plants, nuclear submarines, nuclear aircraft carriers, nuclear cruise ships, not cruise ships that people ride on, but cruisers in the Navy. When they use them up, they have all this waste material that is highly radioactive to store. So what do? They put it into barrels, try to seal it up as well as they can, and then they ship it right. As far as I know, they're going to a place called Green Mountain or White Mountain or something like that in Utah and burying it in deep, deep, deep underground in caves. But here's the problem, folks. The best technologies we have to store and seal this stuff, we don't know how long that lasts because we've never stored it very long. And there's no way to test it. At some point, is that going to eat through all that storage stuff and start leaking into the groundwater? There's a real good chance it will. Okay? And we don't know what to do with it. They put it in there, they seal it up. We can't do much else with it. Brandis is here. Okay? Not a very pretty picture at all. I have my watch, but I forgot to bring it out. What is it, about 3:15? Is that right? Getting close to that? Okay. So, this is a big problem. Not an immediate problem, but it is a problem. Now, actually, shortly after we moved to Birmingham, this is probably about the time most of y'all were born, there was a big controversy because a lot of the nuclear power plants up in the Northeast, they didn't have that facility, they didn't want to ship it that far, and they decided they were going to ship it down to, they heard there were some big landfills. Where was that? Oh, it was some county out in Alabama, Greene County, Alabama. And they said, let's just ship it down there and put it in a landfill. And they actually had the train cars with that nuclear waste on it. And I think they may have even made their way across the Georgia-Alabama line before someone said, time out, folks. No, we're not going to let it be buried in a landfill. Because what if it had been? Then if we had had leakage of any nature whatsoever, everything south of there, and maybe even north of there, because you don't know where the water is flowing. You know where surface water is flowing south, but the underground water could have been coming this way. And no, someone was smart enough to stop them before they got it there. They were going to bury nuclear waste in the landfills in Greene County, Alabama. I'm so glad someone stopped it. Okay. So, what happens? Nuclear fission puts off incredibly large amounts of energy. That energy is then used to heat water in the reactor. That is used to produce steam, super high energy steam, high temperature steam, to turn generating turbines. These are steam turbines, a lot like the water turbines are in the hydroelectric plants, but these are much hotter, much more critical, the tolerances and stuff, to turn these generating turbines, and that produces our electricity. The safety of the nuclear power generation is controversial. I've already been talking about that. What you do with waste, and you better be very careful how you operate those plants, because if they start a meltdown, there's not much you can do. Okay? One person, not too many terms ago, wrote on, what do they call it, the elephant's foot or something like that, which is that big mass of radioactive material left over at Chernobyl that's in there, and nobody can get close to it to get it out and contain it, so it just sits there emitting radiation. So yeah, there's a lot of different paper topics you can choose from. All right, that was Energy Sources Today, 3.4. Read the book, okay? And by the way, they said there is a blurb on the top of page 77. Notice the word fuel here. Grow your own fuel. Okay, yes. I'm sorry. Talking about what? Immigration, you said? Can you connect it to physical science? Okay, yeah, try to keep it something connected to physical science. Yeah. I love reading about immigration. I think that's a huge topic, but it doesn't really fit this course too well. Okay. Grow your own fuel. Remember back on the earlier thing, biomass? Okay, that's, yeah, say again?
For the coal.
Yeah, but not for coal. Burn it earlier, like we used to do burning wood. It's a lot of ash and stuff, but there's are areas that are trying to raise things that used to be useless crops, like grasses and stuff, but that burn really well and fairly cleanly, and, you know, compressing them into artificial logs and stuff like this and burning that. Not as good as coal, but a lot cleaner than coal. So that's, I think, what they're meaning, grow your own fuel. You can read that and find out more. All right, the person behind the science, before we get into the other part, is James Prescott Joule. We've been talking about Joules all term. This is who it was named after. An interesting character. If I remember it right, he was a sickly child. But his father was fairly wealthy, but his father was wealthy not in a very socially acceptable way. This was back in England, when the wealthy people were usually the aristocrats that owned all the land and stuff. Everybody else worked for the nobility. Until industrialization started, and now people were making money in other ways than having lots of land. His father was one of those. He was a brewer. In other words, he made spirits, as in beer and wines and liquors and things like that. That was not considered an upper crust thing to do. But he made lots of money, and soon he was richer than many of these aristocrats that looked down their nose at him. Okay? But he had the sickly child, James Prescott Joule. But he was one bright cookie. So he encouraged him to go on and study, since he couldn't do lots of things. There's some thought that he may have had hemophilia. Y'all know what that is? That's the free bleeders. He didn't have enough platelets or something in his blood to clot the blood. So if he ever got cut, he'd bleed to death, basically. Or if he got bruised, the bruise would keep growing and growing, because he wouldn't, you know. So he had to be very well protected and stuff. I don't know if that's what it was. I read something they thought that's what it was. So he used his mind instead. And he came up with very detailed experiments to do things. And one of these landed gentry nobility type, who was also a very excellent scientist, was named William Thomson. His title was Lord Kelvin. He's the one that the Kelvin temperature scale is named after, by the way. He's the one that came up with the 3 laws of thermodynamics we'll talk about next chapter. He took Joule under his wings and brought him into the Royal Society, which was usually set aside for upper crust people, and said, look, this kid is brighter than any of us. He gets admitted. I said so, you know. So anyway, pretty interesting character there. All right. There's a little blurb also here about myths, mistakes, and misunderstanding the difference between recycling, reusing, repurposing, those kinds of things. I'll let you read that on your own. So now to 3.5, energy sources tomorrow. Now some of these, tomorrow is almost today, okay, because they were written a few years ago, and we have made some advances. What we're looking for now is alternative sources of energies, one that is different from those commonly used today. Now, already we're doing some things like hybrid cars that are improving using current technology, and those are good steps in the right direction, okay? But we're looking for new things. So today we're burning mostly fossil fuels. What was it? Something like 80, 90%, 89% maybe were fossil fuels. That's coal, petroleum, natural gas, huge percentage. Then we also have nuclear, which is sort of new. Falling water, which has been here a while, but that's such a small percentage, like 3%. But that's what we're using mostly today. What are we doing tomorrow that's different? Well, already today, when this book was written, solar was new technology. Now solar is becoming more standard. Like I said, driving to New Orleans last weekend, we saw solar panels on the top of many, many roofs down there. We need to be doing that in Alabama. You know why we're not doing it in Alabama? Because Alabama Power has such a monopoly in the state, they make you pay if you do solar. You know, whereas a lot of other states, if you make it, you get to use it, and you actually get to sell it back to them. Okay? That's in Alabama, not so. Geothermal, we're doing a little bit more of that. We have been for a while, but we're looking into more. The whole nation, island nation of Iceland, as the name implies, that's a cold, cold, cold area. Way, way north. But they spend almost no money on fossil fuels. How do they do that? They're a volcanic island. So what they do, they drill down in the hot volcanic rock, pump water down there, pump it back up, and pump it under the streets and into people's homes, and that's how they heat their homes, using geothermal heat from the earth to heat their homes. Hydrogen gas is another one that's sort of a great idea, but it's sort of hard to put into practice. And then, like I said, we do nuclear right now is fission. We know how to do fusion, but it's awfully expensive to do and really hard to do and really hard to control, too. But we're making some progress on fusion. Okay? So let's look at some of these. One is solar technology. One is solar cells. This is direct conversion of light into electricity. Now, if I'm not mistaken, I think Isaac Newton came up with this idea. He was how many centuries ago, but now we're beginning to put it into practice. The good news here is we are so much better at doing this today than we were just one generation ago. It used to be solar cells were so expensive, so they wore out so fast, they just were not economically feasible. Okay? Nowadays, they're getting much, much better. So people can afford to put them on the roofs of their houses and produce electricity. Now, the thing I described at Georgia Tech, mirrors focusing sunlight to heat water to steam generation, that's called the power tower. Sometimes they're vertical. The one I talked about was horizontal. The sidewalk went right along next to it. You can see it there. Those mirrors capturing that, heating the water that was in the pipe that went down there. Now, there's all sorts of other things we do. Some of this is old stuff, some of it is sort of new, but we need to be doing more and look into more. Passive applications. Designs that use solar energy flow naturally. And I'm really proud, I have nothing to do with it, but I'm still proud, that my father's first cousin, so that's way back, married an architect. She and he both graduated from Duke, the architect and his wife, my father's first cousin. So a pretty sharp character. He was an architect, and way back then, I mean, he's been dead several decades now, but way back when he was doing, every chance he got, he faced the buildings that he was building faced them toward the south at an angle that was equal to the latitude or close to the latitude where he built it. So if it's North Carolina, it might be a little bit, Georgia would be down here. Did that and put a big eave on it. And the reason he did that, in the summertime, the hot part of the day, the sun would be above the eave and not coming in the window. And he had a lot of glass here on this wall. But in the wintertime, when the sun was below that, the sunlight would come in and warm the building naturally. That's passive design. A really great idea. Okay? There are other active applications. Solar collector used to heat water. And this is something, I've heard people talk about it, and I wish I could do it, but it seems like every house, if it didn't have solar panels on the roof, you ought to at least have black pipes through which you run water. Okay, and those black pipes would absorb the heat from the sun facing south and then pump it in and use that as your hot water system. Because actually heating water is one of the most expensive things we do. You don't think about it, but we use it for cooking, for washing clothes. We do it for washing dishes. We do it for showers. We do it for all sorts of things. We are heating a lot of water. That's an expensive process. The sun could be doing almost all of that for us. And actually, some of the places, I think in Florida, I heard some people talking about it. Again, an architect that I worked with down there some said that they were actually, in addition to the hot water heater, I think they actually pumped some into the houses for heating the others. But most of it went to hot water heater. Okay. Now, so solar collection used to heat water like these power towers did, but not that sophisticated, then used for heating or electric generation. Okay. Continuing solar wind energy. Now, back when this slide was done, they were just beginning to have wind turbines. Today, you can go into the Midwest, the far West, and you can see huge wind farms. When my wife and I were like 2 or 3 summers ago, she had professional meetings in Utah, near Salt Lake City, and it was the week between our terms, so we had the whole week. So we decided to go out early, and we drove around, some in Idaho, some in Utah, some in Montana. Say again?
Minnesota.
Not that far, just in that little area. We drove through Yellowstone again, and we had been there before, and Tetons and stuff. But when we were driving in Idaho and Montana, and a little bit in Utah too, we passed just wind farms all over the hills there, because the wind blows pretty consistently out there, and these things were just the farmers were down there still farming the land. The wind turbines were way up here, not bothering them at all, just where the base was. That took up some land. They were still cutting hay, cattle grazing, and stuff like that. So they were still able to use the land as they were renting it out for the wind electric conversion. So wind energy has picked up. Back when this was done, it was still in its infancy. Now it's a lot more common. Now, wind is often inconsistent. Here in the southeast, look at that. The wind is just barely blowing now. Okay? There are some days it blows big time, but it's pretty expensive to do a wind turbine for it to sit there and not turn. Okay? So some places it's inconsistent. But boy, out west, if you've ever been on the Pacific coast, the wind's always blowing there, and they have wind farms all up and down the Pacific coast. Scotland had a big wind farm, and some guy who was building golf courses wanted to have a golf course, but he didn't want the wind farms there, but it was already there. He pitched the fit, but as far as I know, they kept the wind farms there. Okay, I hope so anyway. Okay, but anyway, I won't name who that was. Okay. Biomass, plant material formed by photosynthesis, but you don't have to wait for it to be hundreds of thousands of years to form oil and stuff and pick up other things. Some people, in fact, the country of Brazil doesn't have very much natural oil and stuff like this, and they were wanting to grow their economy, so they started growing extra corn and extra soybeans, not to feed animals like we do mostly, but to make ethanol. And we do. A lot of our corn and soybean production is used to make either oils or ethanol. Okay? Now, I'm going to give you another biomass thing that people have started doing too. Many of you cooks?
Yeah.
Okay? And especially here in the Southeast, we like to deep fat fry things, don't we?
Yes.
Yeah. And you can't use that oil but maybe a time or two before it's really either going to stink like fish or be a little rancid or something. But rather than dumping it out, a lot of places, especially restaurants and stuff, people will come around, pick up that used cooking oil, go out and clean it up some, and make fuel oil out of it. Guess what? You don't have to wait hundreds of thousands a year. It's right there. Use it. It's already been used once. Reuse it. Okay? Burn directly or converted to other fuels, like ethanol. That's another one. Okay? And a lot of the gas you buy these days at the gas tank is 10% ethanol. So we're growing some of our own fuel. We're not counting just on fossil fuels. Now, any of you know what a problem with ethanol is? There's something about the way ethanol, because it's an alcohol, burns, and also it just does. It eats up plastic pretty badly. And a lot of your internal combustion engines have a lot of plastic where they used to have metal parts because it's cheaper. But those parts of the carburetors and other things like this, they get eaten up by ethanol. So there are some problems with it, but hopefully we can take care of those. Now, this to me is pretty weak, but I guess it's important. Agricultural and industrial heating. Why don't you use more sunlight to dry grain, dry fruits, dry cure paint, do things like this, rather than using a fossil fuel to heat it up? It may take a little longer, but look, it's free. Okay? This is one that I find, wonder how it really works. Ocean thermal energy conversion. It uses temperature differences between surface and ocean depth. Like I said, the Gulf of Mexico can be 80 degrees here and 32 degrees down here. But that's miles apart, a mile apart. So how do you use that to generate electricity? Maybe there's a good way, I don't know. But my question is, why in the world aren't we using the tides to do this? There's some places the tides come in and out. They move a lot of water back and forth. Why don't they have turbines there being turned by the tides? Because that's going to happen every day, twice a day, every day. It doesn't count on wind or anything else. It happens in the daytime, it happens at night. So there's probably a lot of things we could do to improve. Geothermal energy. Now, some of these percentages I find hard to follow, but I think I finally figured them out. Now, geothermal energy, if you think back to the earlier slide, that's 2 or 3%, something like that. Pretty small amount of geothermal energy. Maybe getting a little bit more. But a lot of this is hot, dry rock. That's about 85% of the geothermal energy that we do is from hot, dry rock. Like I said, in Iceland, they drill down into the hot rock, pump water, and then pump it back out in other people's houses. Okay? Good way to do it. Okay? Always associated with volcanic activity. Here in the Southeast, we don't have a lot of volcanoes, do we? As in none. Okay? In the Pacific Northwest, yes. Okay? They have some. Many of them are not active, thank goodness, but some of them could be sort of. Hawaii, I bet you they use a fair amount because that's a volcanic island. Okay? So, hot, dry rock would be the way. Now, they have had some problems. In Iceland, one time they drilled down to pump water in. They happened to hit a weakness in the rock. And they almost had a volcanic eruption right there where they were drilling. Let's not drill there anymore. Okay. Now, another thing is geopressurized resources. Okay, not hot, dry rock, but geopressurized resources. What do we mean by this? Underground reservoirs of hot water containing natural gas. Maybe pull the natural gas out and maybe use the hot water itself. Okay, this is 14% of the geothermal energy. Now, the only place I've actually seen this, I'm sure there's some other places, is in Yellowstone. You know, it's not Jellystone, it's Yellowstone. That national park out in, mostly in Wyoming, but a little bit in Montana. The geysers, hot water coming off of hot rock. And now that we use them, we don't use them, but we look at them and just are amazed by them. In some places, they actually use them to generate electricity. And maybe even around there, I don't know. Dry steam is very rare, only 3 sites in the U.S., and I bet you they're all somewhere out there near the volcano. Now, hot water, though makes up most of the recoverable geothermal resources, can be circulated directly into homes, businesses, farms. That's what I described in Iceland. There are other places. There's a place in Georgia where President Roosevelt, Franklin Delano Roosevelt, went because his polio, you know, he was uncomfortable. It was Warm Springs, Georgia. Okay? I hope that if they can get that naturally occurring warm water, pump it into people's homes. Let them heat their homes that way and save on fuel. Okay? There are other places. Banff, Canada, had hot springs there, and that's pretty cold up there because the hot springs are hot. In Yellowstone, you could see it. There was steam coming out of these pools of water, and they said even in the wintertime, snow everywhere else, the buffalo would be there in the hot springs just having a good old time, you know, because it was very, very pleasant. So if the buffalo have enough sense to do it, why don't we? Okay. Hydrogen. Now this is one that I'm a little skeptical on. Hydrogen. Okay. Fossil fuels you burn, right? And they give off carbon dioxide, which is a greenhouse gas, and then you have all the ashes and other pollutants. Not the best thing to burn. Hydrogen, when it burns, however, what's the byproduct of hydrogen when it burns? No carbon dioxide at all. Okay, oxygen is what is used to burn it. What comes out when you burn hydrogen and oxygen? Water! How much cleaner of a fuel can that be if its byproduct is water? Okay? You can't get much cleaner than that. Now, so hydrogen is a very clean burning fuel, and it's a very good burning fuel. Anyone ever hear of the Zeppelin or the Hindenburg? Okay? What was that? One of the earliest blimps. Blimps were the lighter than air craft before we had airplanes. The only way people could do air travel. These big blimps. Well, the lightest gas that we have is hydrogen. So the original blimps were filled with hydrogen. Until one day, they still don't know exactly what happened. Either it struck something and there was just enough friction to tear the skin and also heat it up, or it was struck by lightning. They don't know which. But something happened. When that happened, the hydrogen started burning in oxygen all around, and it was one big fireball. They decided not to use hydrogen anymore in the blimp. Now they use helium, which is the second lightest gas ever. It's heavier than hydrogen, but it's still very, very light, and that won't react to anything. So all the blimps you see today have helium in them, not hydrogen. Okay? But hydrogen burns like crazy. Okay? Now, they say, here's the problem. There's several problems with hydrogen. First, how do you get hydrogen? If you take the air that's in the room or out there in the naturally occurring, and you were to extract all the hydrogen, you'd have just a little bit. Because hydrogen is very, very, very reactive. So you have to separate hydrogen from whatever it's combined with in order to isolate hydrogen. Well, guess what? that takes as much energy to separate it from what it's combined with than you're going to get out of it when you go to burn it. So overall, it's not a net positive process. It's either neutral or negative. There were actually some guys over there in the automotive department, this was several years ago, probably 5 or 6 years ago, that were trying to find a way to burn, to hydrolyze water, which when you hydrolyze it, it is hydrogen gas and oxygen gas, okay? And then capture the hydrogen gas and then use it to burn it. Well, the trouble is it takes just as much energy to hydrolyze water as it got energy to reburn it again. In fact, you always wind up losing a little bit of energy. So even though it was a great idea, it was net energy expensive, okay? But it's clean. Boy, is it clean. The combustion byproduct is water, okay? You can not get much cleaner than that. Now, here's other problems. Not only is it expensive to extract hydrogen, the other possible problems are, how do you store hydrogen? Like I said, it's the lightest gas, the smallest molecules, single protons with one single electron. You can't get much smaller than that, okay? How do you store it? It goes through just about anything. If you have rubber pipes, it goes through those. If you have steel pipes, it might have trouble, but it will leak through something. And what's more, you have to pressurize it because it's such a light gas. It takes up an enormous volume, so you have to pressurize it. The more you pressurize it, the more it leaks, okay? And if it leaks and catches fire, it explodes, okay? Extremely flammable. That's why we even want to burn it, okay? So, it's better to store not as a gas, pressurized, but as a liquid. But you know how cold you have to get liquid hydrogen? Down just a few degrees above absolute zero. And that takes more energy to cool it than you get out of it when you burn it, okay? So, yeah, there's some pretty big problems with hydrogen. Now, there are some things people are working on. They're called fuel cells. And what it is a process that takes something that's a hydrogen-rich compound that's probably fairly cheap, and then chemically extract the hydrogen, which is not that expensive a process, and then burn it immediately, okay? And that is a net energy positive process, and they're looking into doing that. You can do it on a small scale. It's sort of hard to do it on a big scale, though. Oh, that was our last slide, wasn't it? All right. Let's see what else is in the chapter here. Oh, and I'll say this every chapter, and I'll say it again. Nothing replaces reading the chapter. Best idea is to read it before I talk about it, and then whatever I'm saying and you see on the slides will make more sense to you. But even if you don't do that, read it afterwards, okay? There is a summary at the end of the chapter that has a lot of italicized words. These are pretty important ones. It doesn't capture everything, but it captures a lot of the important concepts. Then you have a summary of equations. There are only 5 in this chapter, but some of these can be manipulated to form other equations. Key terms. Not as many as most chapters, but you'll find most of these were the italicized words in the summary. They list the page where they were first described or defined, listed alphabetically, but they put the page number with it too. Then I think the best thing to study for your test are your applying the concepts. Now, they only have 36 questions here. That's fewer than most chapters. But if you know these same questions won't be on your test necessarily. But the same topics will be, things will be turned around, twisted a little bit. Same topics. If you know these 36, you have a real good chance of getting a very good score on your test. They provide the answers to them too. So if you have any question, how in the world did they get this, bring those to class and we'll talk about it. Questions for thought. This is again only 12. Most of the chapters have more than this. But however, for further analysis, there's 9, which is more than most chapters. So there are quite a few questions there. Invitation to inquiry, you might want to look at that if you'd like. The parallel exercises are more like the examples we did in the text. There's Group A and Group B. If you have a big book, I know the Group A answers are in the back. I requested they put them in the small books, but I haven't been able to find it because I don't have a small book. But I've been told by students they don't think they're in there. Okay. So since we did finish the chapter today, the lab we do today will be on energy. I think that's the second lab and the second lab we'll do in this chapter. And then we'll get started on heat and temperature. How much time do we have? About half an hour? Okay, we'll get started on chapter 4. And then we'll continue chapter 4 on Tuesday. We'll only do 2 hours on Tuesday. Then we'll have the first lab for chapter 4 on Tuesday. And then we'll have the test on chapter 3 on Tuesday. Everybody hear that and understand it? So we'll do the last lab in chapter 3 today. We'll start chapter 4 today. We'll continue chapter 4 on Tuesday. Have the first lab from chapter 4 2 hours in. And then when you finish the lab, you can do the test from chapter 3. Okay? Today is a very short lab, so most of you will probably be going home a little early. Too bad Wesley's not here. He always likes to go home early. Today he would have had a chance, but he didn't make it. So anyway, let's move on. So that's it for chapter 3. Let's go to chapter 4. All right, chapter 4. Get it set up from the current slide. A couple of different things about chapter 4. Most of our other chapters have been dark print on white background. For some reason, this is light print on brown background. So if I'm doing problems, I have to use a different color for you to see it. Okay, but it's pretty easy to do. Chapter 4 is heat and temperature, which is a very good chapter to follow chapter 3, which was energy. Okay? Because guess what? Heat is, in some senses, a form of energy. We talked about it earlier, heat engines and heat things. Okay? So heat and temperature tie in nicely with that. The reason, probably the major reason that separated, for many years, okay, Isaac Newton came along and developed the laws of motion, that kind of thing. And that sort of got science, he and Galileo, got science started. And then people had to figure out things. Well, Newton had talked about forces, he had talked about momentum, he had talked about those kinds of things. But people really didn't have a good idea of what energy was. They did know what heat was, because long before Isaac Newton, people had been burning fires and, heating things. They knew what heat was. And the earliest ideas were that heat was some type of ephemeral matter that existed in things. Okay? For instance, wood. If you think about it from an ancient point of view, you took wood, you lit a match to it, or did whatever it took to get it burning, and it burned and released heat, and what was left was ash. Not nearly as much as what you started with. So people were thinking heat is some sort of material that changes and disappears as it becomes heat. So they thought heat was one of the basic elements of matter. In fact, if you go back to Aristotle, he said there are 4 basic elements: earth, water, wind, and fire. 3 of those made a singing group back when I was growing up. Earth, wind, and fire. Okay, good. Had you heard of them? All right, good deal. Okay. Throw in water and you got Aristotle's 4 basic elements. Well, guess what? None of those are elements. Okay, earth is a mixture. Water is a compound. Wind is a mixture. It has some elements in it, but it's not by itself an element. And fire is not even an element. It's not even a material. it's a form of heat energy. So that's why heat was treated separately from energy, because it was a long time. In fact, it was James Prescott Joule that finally came up with the mechanical equivalent of heat. If you read back in that, you probably find that. Okay? So here we're talking about heat and temperature. Is that redundant? Are they talking about the same thing? Is heat the same as temperature? No, not quite. They're related, sure, but they're completely different different things. Okay? So here's the core concept. This is on your page 87. A relationship exists between heat, temperature, and the motion and position of molecules. Whoa here. When we think of heat, we think of something macroscopic, something you can feel, something you can sense. When we think of temperature, we think of something you can measure. Okay? Related somewhat to heat. But then the motion position of molecules, you can't even see a molecule. Okay? You can't touch a molecule and know that you're touching it. They're submicroscopically tiny. So what is the relationship between these big concepts, macroscopic concept, and the microscopic concept of the motion and position of molecules? That's what we'll be investigating in this chapter. So here's the overview. You probably can sum it up in one word, or if you could, the closest you could get to it was thermodynamics. Thermo, of course, means heat. Dynamic means change. Changing heat. Dynamical. Things that are changing. And what we're going to do here, we're going to study the macroscopic, the big scale processes involving heat, mechanical, and other forms of energy. Okay? That's going to be the first part. And that's basically what thermodynamics does. It's the study of macroscopic processes. Now, we'll talk about a few applications of this. Systems with energy inputs and outputs. These would be your heat engines or your heat pumps. One of them is taking energy, taking heat, and making another form of energy. The other is taking another form of energy and creating heat or removing heat. That would be refrigeration. A heat pump and a refrigerator, air conditioner and a heat pump are basically two different sides of the same coin. Okay? Now, thermodynamics is based on, but not concerned with the microscopic processes. It's mostly macroscopic. Okay? So what will our approach be? Our approach will be to discuss the underlying microscopic processes and then build up to relate the microscopic to the macroscopic and study the law of thermodynamics. So we're going to start small, go bigger, and then bring in thermodynamics. So they sort of got the slide backward. I would have put this over here, that over here, but they chose to do it this way. Okay? So, where will we begin? By the way, in the text, this is on page 88. Kinetic molecular theory. Okay, let's talk about this. First, molecular means incredibly small scale. Okay? Molecules. Okay? These are things made up of just a few atoms. Okay? Incredibly tiny. Kinetic molecular theory means the movement of molecules. Kinetic or kinesiology is movement. Okay? So here the collective hypotheses for this theory are about the particulate nature of matter and the space surrounding that matter. Okay? Now, we've hit this before. We've hit it before. We'll probably hit it again. We talk about the ancient Greeks. Now, this is long before Newton and Galileo. Way before that. Newton and Galileo were, 1400s, 1500s, something like that. These are talking, that's AD. We're talking about the Greeks. BC, okay? 2 millennia before before Galileo and Newton. And one of these Greeks was Aristotle. We mentioned him before. But we're actually going back way before him. This was a couple of generations before Aristotle. Maybe 3, 4, 5 generations, but it was well before Aristotle. There was a guy named Democritus, a Greek philosopher, coming close to being a scientist, but not quite. And he had this idea. He said, what if you had a piece of iron or copper or whatever you had, some metal or some material. And what if you broke it into two? Then you had smaller pieces. Take the smaller piece and break that into two. And then take the smaller piece and keep breaking that into smaller and smaller and smaller and smaller pieces. Now, this is just a thought experiment. He didn't actually do it, but this was his thought. He said, at some point, you have to get into the smallest particle you can have of that material that you couldn't break any further. And he said, he named that an atom. Because in the Greek, that came from the word that means indivisible. You can't split it any further. Okay? That's where the concept came from. Okay? Earliest ideas on atoms. But along came Aristotle, who was the brilliant sort of scientist of all the ancient Greeks. And Democritus has been dead probably for many years now. And he said, nah, he was wrong. He said, matter is a continuum. No, you can't get it to its smallest piece. If you get to the smallest piece, you can still get it smaller and smaller. It's a continuum. It has no end. I don't know where he got that idea, but he said it. People believed it, so people gave up on the idea of atoms just within a few generations of when it was proposed. Well, we can blame Aristotle for this too. Remember what his 4 elements were? Earth, water, wind, and fire. With fire not even being a material. But, just think about those. Earth is always out there, basically free. Water is always out there, basically free. Wind is always out there, basically free. And fire, you might have to spend a little bit to get it, but it's pretty cheap, right? Well, these Europeans, studying when they finally woke up in the Renaissance and went back and learned about the ancient Greeks' writings and stuff, they said, hey, wait a minute here. If these are the 4 basic elements of nature, which Aristotle said, and everybody believes everything Aristotle said, and guess what, folks? If we can combine these really cheap materials together, heat them and grind them and push them, doing all this stuff to them, dissolving them, re-solidifying, doing whatever do. If these are the 4 basic elements, we should be able to, in some combination of them, come up with pure gold. And then we'll make a killing. Okay? Or come up with pure silver. Or come up with any of these more expensive materials. If that's all there is, earth, wind, water, and fire, we can combine those together to get these other things. So let's get to looking. So that's what they did. Okay, now this is getting into a little bit of chemistry here too. And they started doing it. After a very short time, they said, hey, we better keep good records of this because we're doing the same thing over and over. So they started being very careful in their measurements. Let's take so much of this and so much of that, heat it to this temperature, grind it to this fineness, see what we get out. And in doing this, and these were, by the way, they gave them a name, these were called the alchemists. Okay? That's where we get our modern day chemistry from. The modern day chemists don't like to be too much associated with it. But they were trying to get rich quick. That's what they were promoting. Okay? And actually, Isaac Newton was one of them. He really got into alchemy. He was trying to find, because he was a scientist, he was just trying to find what makes things work. And as they did, they found out, that's where the current view started coming into play. He said, this can't be all there is. Because we're finding all these different materials here that we can synthesize and pull out and stuff. And finally, a guy named Lavoisier, he was a Frenchman. He compiled the studies from all these other alchemists, all their careful notes and stuff, and he came up with a list of about 37, I believe it was, basic elements. And basically hit most of the biggies, okay? Now, some of you, I think all your books have somewhere in the back or somewhere a periodic table. And of his 37, he probably had 30 to 35 of the top, maybe 40, okay? Not all of the ones on his list were actually elements. He still had caloric there, which is heat, which is not an element at all. And he had some of the oxides that he didn't know, like calcium oxide and stuff, that he didn't know how to split up any other. But he had a pretty good list, okay? So the current view is that matter is composed of microscopic, I would say sub-microscopic particles called atoms. And there are only, to our knowledge today, a few more than 20. Your periodic table, not 20, 120, I would say. Your periodic table in the back shows 118. Okay, now not all of these are named. Not all of them we're real sure exist, but they have room for at least 118. There may be more. You might have to add another row to the periodic table, but those are the only ones we know of so far. Okay? So, matter composed of microscopic, I'd say sub-microscopic particles called atoms. Atoms combine to form molecules. That's what we're studying, kinetic molecular theory. So atoms combine to form molecules, and many of the macroscopic, the big scale phenomena can be traced to interactions on the microscopic, sub-microscopic level. That's what we're going to hit at first. How are we doing on time? Okay, got a few minutes. So let's go to these molecules. All right. Now, molecules is a microscopic, sub-microscopic concept. Okay? This slide sort of ties together these macroscopic and microscopic concepts. They start with chemical elements. But a chemical element, now that's a macroscopic concept. The elements: iron, hydrogen, helium, oxygen, nitrogen, aluminum, iron, cobalt, nickel. These are all macroscopic concepts. These are your elements. They're defined by each unique type of atom. As I said, the very lightest atom that we have is one proton and one electron. That makes hydrogen. And that's what hydrogen usually is. Now, we'll talk in the chemistry chapter about some slight changes to that. But if you find an atom anywhere that only has one proton, that's hydrogen. Got to be hydrogen. No other choice. If you find an element that has two protons and only two protons, may have a few neutrons, that's okay, and it always will have some electrons, but two neutrons in the nucleus, that's always going to be helium. 3 will be lithium. 4 will be beryllium. So these elements each have just one type of atom, always the same number of protons. That's what makes a chemical element. Now, what is a compound? Again, a compound is a macroscopic concept, just like element is. But now we're talking about pure substances, but they're made up of 2 or more atoms chemically bonded together. Now, we won't even, in the chemistry part, be able to talk too much about the chemical bonding, but I'll introduce you to it as we go. But one compound is water. And someone's already said it's H2O. 2 hydrogens, 1 oxygen, to form a brand new material called water. And if you think about how weird that really is, remember we said hydrogen was an incredibly explosive, flammable gas, right? The Hindenburg, okay, blew up big time. I mean, burn like crazy, okay? An explosive gas. Combine that with another gas, oxygen, that is necessary for anything to burn. Nothing will burn unless oxygen is present, okay? So here you have an explosive gas combining with a gas that produces combustion, and somehow you fix those together, and what do they form? A liquid, water, that you use to put out fires. Isn't that crazy? You see, this liquid water has completely different characteristics from either the hydrogen or the oxygen. Totally different. Completely different. Okay? So that's what a compound is. Pure substances made up of two or more atoms chemically bonded together. And when it says chemically bonded, it changes everything about it. Okay? Everything about it. So, compounds, that's a macroscopic concept. Elements, macroscopic concept. Elements made out of unique atoms, microscopic, submicroscopic concept. Compounds are made up of pure molecules. Macroscopic, microscopic. The smallest unit retaining the properties of a compound. That's a molecule. One molecule of water is two hydrogen, one oxygen bonded together, chemically bonded together. So it's nothing like hydrogen or oxygen. It's a brand new material. Molecule. The microscopic concept of the compound. Okay? Now the shorthand here, molecules can stand for either atoms, monatomic molecules, or molecules, which are multi-atomic molecules. So sometimes we use molecules when we're really talking about atoms. It's okay. Now, what are some of your molecular interactions? Most of the time, these are attractive interactions, causing materials to cling together, such as hydrogen combining with oxygen to form water. Okay? That's an attractive process. Now, we use some terms to describe that. If it's two materials that are similar to each other, we call that cohesion. The attractive forces between like molecules. And one of the molecules that is very cohesive with other molecules like it is actually water. Now, I can't remember, we haven't done an experiment with water, have we, in the lab? Okay, we're going to do one later. I'm pretty sure we will. We did one in the last class. Remember when we filled the container with water? I said, keep putting it in, and you actually found water.
So that was the last class?
Huh?
That was the last physical science class?
Yeah.
I was about to say they're running together.
Yeah,
exactly.
exactly.
I was like, I thought we have, but it was the other one.
Yeah, it was the other one. And we'll do it in this one too, I'm pretty sure. We have an opportunity to do that sometime in this class too. And you'll see, yeah, we will. I think in the lab we will do. That's water molecules hanging on to other water molecules. Do this at home, but don't get mama upset or anything. Keep it near the sink and keep putting water into a glass. And keep putting it in until it looks like it's full. Keep adding a little more, You'll see the water actually mounds over the top of the glass. You probably have noticed this before. It actually will do that. And at some point, it will break and go. That's called surface tension. That is cohesion, attractive forces between like molecules. Now you have other, it's called adhesion. That's attractive forces between unlike molecules. For instance, that water wetting your skin, okay? You put water on your skin and it'll wet the whole skin, right? Unless, of course, your skin is oily, and it may not, okay? If you've been working with grease or something, the water will beat up. It won't wet as well, okay? So adhesion is the attractive forces between unlike molecules. Water wetting skin. In fact, that's where we get our term adhesive, is glue. The glue mechanism that really sticks things together. Don't ever play around with super glue and hold your fingers together. You're going to have pretty bad sore there when you cut it apart. It's awful. Okay, I haven't done it, but I've heard that. Okay, Sometimes your interactions can be repulsive, like I just mentioned, water beating up on wax or oils. It'll do that. They don't mix. They're not adhesive or cohesive. They're repulsive. Okay? It doesn't happen as frequently, but it does happen. Okay? All right. I think the phases of matter part is going to need to be pretty much together. So I think this may be our stopping point. I know we're stopping a little early, but y'all need to take a little bit of a break, I'm guessing, right? So let's just pause here, and that will end the lecture today. And one reason I am stopping a little early is I took the lab down to be copied this morning, and I haven't had a chance to get back to the copy room to pick it up. So I've got to go down there and pick it up. And then we will be in 259, the place where we were, not the last lab. Last lab we were all over the building, remember, doing stairwells. The lab before that, when we did the balls rolling against each other, that kind of stuff, down in that lab, 259. So don't have a marker in this room. So I'll put a note on the board for people like Austin who may be coming in late. So I'm going to pause this. Got some more to go. Okay. What we've done so far, each team measured the mass. What was the mass?
0.5.
0.5 what? Kilograms, okay? And then each team measured the minimum distance from the floor. I won't ask that because that varied from team to team. And then you subtracted that number from 1 meter when you put the mass at the top of the meter stick, and that gave you your delta H. And then from that delta H, you calculated the GPE at the top, mg times that height, delta H. Then you looked at the velocity. The velocity of the top was 0. And so what was the kinetic energy at the top? 0, because it's 1/2 mv squared. If v is 0, kinetic energy is 0. Then what was the mechanical energy at the top? Okay, different teams have different answers, but it's going to be whatever the GPE was at the top, because kinetic energy was 0 at the top. And mechanical energy is kinetic energy plus potential. All right, then at the bottom, what was mechanical energy? It was that same amount that it was at the top, because mechanical energy is conserved. Okay? The GPE at the bottom, though, was 0. And the kinetic energy at the bottom was your mechanical energy, whatever that was. Okay? Now the question is, what's the velocity at the bottom? Now you just told me you got a number for it, what kinetic energy is at the bottom, right? So I'd say flip your page over and write down the formula for kinetic energy. What is the formula for kinetic energy?
1/2.
Okay, exactly. And you know that's equal to, and you just wrote on the other side what kinetic energy at the bottom was, whatever it is on your experiment, right? Okay, so you have to solve that equation for V, which is something very similar to 1/2 mv squared. mv squared, 1/2 mv squared. Okay, and you have to solve that for V. We did something very similar to it in class. First thing you got to do is
Times 2.
times 2 to get rid of the 1/2. So you double that kinetic energy at the bottom. Then you
Divide M.
M, and what was your M?
0.5.
0.5. Okay, kilograms. And by the way, what was your units for kinetic energy? Units for kinetic energy?
Joules.
Joules. But what is a joule in basic terms?
Kilogram.
Kilogram
M squared.
per second squared.
Yeah.
Yes. M squared per second squared.
Yeah.
So when you divide by 0.5 kilograms, you also lose the kilogram in the kinetic energy. So now you're left with M squared for V squared. Meter squared per second squared. Okay, now how do you get from, now what are you left with on the left? V squared, and you got some number on the right. How do you get to V? No, you don't. It's already
Um,
squared.
You take the square root.
Take a square root. Okay, so you do that on the calculator. Okay, now,
And that be meters squared per second squared.
no, because you take the square root of the units as well.
So meters per second.
Meters per second, an excellent unit for velocity. Okay?
3.6.
Huh?
3.6.
Okay, whatever yours is. Different teams have different things. Okay, now, that's the first part of the lab. That was pretty easy, wasn't it?
Yeah.
All right, we're going to do the second part now, and I think we'll probably use this one because this one keeps bumping into that. So I need two people to man the meter sticks. One over here and one over there. Okay? All right, you're going to do that one? Yeah, I would suggest maybe getting up and moving a little bit because this is probably going to hit you. Okay?
And you got the measurements.
Okay, let me move this out of the way just so it won't. Let me see. I think we'll be safe here. Okay. Need somebody with a meter stick over here, though. You want to man it or somebody else? She's getting rid of all her valuables so it won't get bashed. Okay. Now, if I can get down here, that's the easy part. Getting up is the hard part. Okay. I need one of you two to hold this on top of your meter stick. Keep the stream taut. Okay? Now, I'd flip it over so over that. This way. Yeah. So that you're measuring from the floor. Okay. Back just a little ways here. Okay. Ooh, not that far. A little. Okay. Yes. I think that's pretty good. So y'all watch here. Austin is going to release his from the top here. You tell me about how high it goes there.
Okay.
Okay? Y'all watching?
Me or that?
Huh?
I'm gonna.
You're going to just release yours, and they're going to estimate how high it goes over there.
Okay.
Ready? Anytime. About how much? About a meter, isn't it?
About a meter, yeah.
Okay.
1 meter.
All right, you can stop it. Okay. Now, it went to about a meter. You kept going almost a meter each way, right?
Yes.
Okay. Now, what I'm going to do, I'm going to be the peg. Okay. And what I'm going to do is hold my finger here as the peg, and then you're going to release it, and y'all are going to look and see about how high it goes on the meter stick when I peg it about a third of the way down. Does that look about right?
Yeah.
Okay. Release anytime. How high did it go? Do it again.
90.
Well, let's do it
90.
again. Approximately. Okay.
Something 90.
I went all the way.
Yeah, we're pretty close to a meter again.
Yeah.
Pretty close to a meter. Okay? Now I'm going to peg it about halfway down the string. Okay? About right here.
2/3. Okay, that was at like 90.
That's, well, let's try it again.
That's 80.
Well, my finger.
Yeah, still 90.
He wants to be.
Awful close to a meter. Maybe not have quite made it, but pretty close to
So
a
it
meter.
goes all the way.
Okay. Huh?
Goes all the way to the top again.
One more time. Okay?
Won't be at the 2/3, right? It didn't go to the top. It was
My
at 90.
peg is sort of moving on me some. Okay? So that was close to a meter anyway, right?
Yep.
Now, I'm going to peg it 2/3 of the way down. Well, okay. 2/3 of the way down. Y'all observe what happened.
I thought
Oh!
you on 8 or 9, sir.
Huh?
You on 8 or 9.
I said it was close to a meter. You can put 0.9 if you want to.
Okay.
Okay, what happened then?
Flip, wrap around.
Oh, it wrapped around the peg. Okay, now I'm going to see if I can get up. Okay, you can get up. Thank you.
Yes.
So, your answer to number 6 was
1 meter.
close to a meter. Number 7 was
1 meter.
close to a meter. Okay, maybe not quite, but close to it. But what happened in number 8?
It wrapped.
You wrap around your arm.
Wrapped around the peg. Okay? Now,
There you go.
that's the first question. What happens at this point? It wraps around the peg. If you want to write that above the line, but
Wrap around.
below the line it says Y. Why did it wrap around the peg?
You move too fast. I couldn't even see it.
Okay, did you want to do it again?
Let's do it again.
Okay.
For explanation of why.
No, I'll go that far. Okay.
I would say-
Yeah, it's just making me go up and down. That's all you're doing.
Alright.
2/3 of the way is about here.
Yeah, right there.
Whoa!
Because you. Alright, do it again.
Try again.
Yeah, get the explanation of why.
It wrapped around the peg. The question is why.
The mass.
It had the same mass all 3 times. And in fact, the first time when Austin did it by himself. All right?
There was a finger hole in it.
What's that?
There was a finger hole in it.
Well, there's finger on the first 2 too, weren't there?
I don't know. Yeah.
Why did it wrap around the peg on the 3rd time? It was 2/3.
Because does it mean
You went lower.
Yeah.
Okay, and what difference does that make?
Like the height got lower.
Okay, and what difference does that make?
Gravity.
Okay, gravity was involved in all of them. Okay, speed has a little
Speed.
something to do with it.
The velocity.
Okay, what is velocity related to? Which kind of energy?
Potential.
Potential. No, it isn't.
No, kinetic.
Kinetic. Okay,
Kinetic.
it's always something
No,
into it.
yeah, potential.
Okay.
Gravitational.
Yeah. Okay, and that's getting real close to it. Because the first time when Austin did it himself, it went back to a meter both ways, didn't it?
Yeah.
Because when it was going, when it got all the energy was gravitational potential energy, that's right when it reached the meter, and then it was all kinetic at the bottom. We did that before, right? And then it was all gravitational potential. So when it got to a meter, all of its energy was gravitational potential because the velocity went to 0 because the kinetic went to 0. And when I did a 1/3 of the way down, it went back to a meter. It all went to gravitational, no velocity there. Okay. When I did it halfway down, it just made it back to a meter because it just did enough energy to get the gravitational being all gravitational, 0 velocity. But when I did down here, one of you said it. Okay, pretty close to it. There wasn't enough cord for it to get back to a meter. So if it couldn't get back to a meter, it couldn't lose its kinetic energy into gravitational potential. So since it still had some kinetic energy, it still had speed, velocity, and therefore it wrapped around the peg. Does that make sense? Okay. All right. Now, what conservation principle does this experiment demonstrate? Something was being... Oh, I'll let y'all finish writing. Sorry. In the first part, and in all 3 parts of the second part, something was always conserved. What was that? Which kind of energy?
Wait, we said
Second?
what conversation? Kinetic energy.
Oh, kinetic energy. I thought it was 0 up here. Huh?
Potential.
Potential, it was 0 down there.
Gravitation.
Mechanical.
Yeah, gravitation. Mechanical.
Mechanical energy.
That's it.
All right, y'all.
We only had 3, name the other 2. So yeah, we got it right.
Thank you.
Okay. Now, we're finished in here. So let's go back to the classroom out here. And there's one more part of the exam.
There you go.
I mean, no, one more part of the lab.
Let's say, calm down.
Okay.
Is somebody leaving their phone in here?
Okay. And a calculator too. I think Bree
Somebody leaving their phone?
and the calculator. Bree, was this your calculator too? Okay. All right. So we're up to team 1. I need to see your paper just temporarily. Okay. And someone from team 2, paper temporarily. Yeah. Okay. Now, for everyone, I can't remember which team was which. For everyone, okay. Y'all filled in the blanks really nicely. I hope everybody have 0.42 on their minimum displacement, in the margin write 0.24. And for those who had 0.24 as their number 2, you write in the margin 0.42 and redo your calculation. Redo your calculation, not, hey, what did y'all get for this? No, that's not what I want you to do. Redo the calculation. What we just did.
So we both gonna have the same calculations at the end.
Well, you should. Or
Yeah,
close
both
to it.
like both teams gonna have the same
Yeah.
calculations.
Right.
Alright.
So those who had 0.4. Okay, if you had 0.42, then 0.24. And if you had 0.24, it's now 0.42. And then go back and do the calculations for 3, 4 parts of 4, 4 parts of 5. Does that make sense? Any questions? Okay. And then for the last 30 minutes,